Hi everyone, this is going to be a video walkthrough for question 1 on exam prep week 13, which is covering more sorting, and this question specifically is on sorted runtimes. Okay, so when we look at this question, the first thing we should note is that we want to sort an array of n unique numbers in ascending order. Okay, so we have some sorting algorithms outlined for us, and we need to figure out the best and worst case runtime of each. Okay, so the first one is that once the runs in merge sort are of size n or of size less than n over 100, we perform insertion sort on them. Okay, so in order to solve this question, let's first recall how insertion sort works or merge sort works. Okay, so if we look at merge sort, we have this merge sort function. This is just going to be some pseudocode to, like, I don't know, refamiliarize yourself with how merge sort works. Okay, so what we do is that we call merge sort on, actually merge sort always takes in a list on the left half of the list. Okay, and then what we do is we call merge sort on the right half of the list. And then we merge the left and the right. Okay, so in this question, we could think about this list as a run. Okay, that's like what a run means. So for some context of what the question is saying, it's stating that we start off with a run, that's the entire list. Okay, so let's say this is my list. Right, the first run we have is the entire list. Okay, this is the second run. Okay, or the second pair of runs are going to be half the size, right? And then we could see, and so on, right? We keep kind of breaking these runs into smaller and smaller runs. And usually what happens is that we keep breaking up the runs by half until the size of the run is 1. Until size of run is 1, right? Upon which this is the base case. Base case. Okay, so for this question, what we're going to do is the base case, it's not exactly a base case, it's more of the point that we stop recursing is going to be when the size of run is less than or equal to n over 100. Okay, that's the point when we're going to stop recursing. Okay, that's just like a quick explanation of what the question is even asking us to begin with. So with this in mind, let's recall how the asymptotic tree looks for a merge sort. Okay, so the first time we call merge sort, our input size is going to be n. We call this input size. Okay, and then in the middle, I like to put my work done for this call, for this function call. Okay, so the first time we call merge sort, right, we have 2 recursive calls, and then we merge the left and right together, right? The merging operation is linear. So we're going to see here that, let's make these in different color just to make it look cooler. Okay, that the work done for this function call is n. And what you guys will notice is that, I can make a better circle than that one. Okay, so what we'll see here is that we will get this following tree, right? So in this tree, we will notice that it kind of looks like this. Okay, this is like the tree that's traditionally there for merge sort. Okay, I'm going to draw one more layer just to be a bit more rigorous. Give me a quick sec. Okay, so my drawing skills are kind of lacking right now. Okay, give me 1 second, 1 second. We're getting close. Okay, so we have this tree, and what we will notice is that the work at each level, let's use a new color just because we're going to make this as egregiously colorful as possible. the work per level is going to be n, n, and n. So we see here that in merge sort, we always have n work per level, okay? And traditionally in merge sort, we have a total of n, just kidding, we have a total of log n levels, each doing n work, which gives us a runtime of n log n. So the difference here is that we're not necessarily having log n levels. So how many levels are going to be in the tree if the tree kind of gets cut off early? Okay, so what we will notice is that this tree is going to stop when n is going to hit size 128. Okay, this is the first time that n is lower than 100. And the quick justification is we'll see it'll be n over 16, n over 32, n over 64, and then n over 128. Okay, so after we get to this point, instead of continuously calling merge sort, what'll happen for every single node at this level, okay, for every single node at this level, it's going to be running insertion sort. Okay, so all of these nodes are going to be running insertion sort. Okay, so with this in mind, I'm going to break up the total runtime into two parts. Okay, it's going to be the merge sort runtime plus the insertion sort runtime. Okay, so we notice here that the total amount of work that we're doing in merge sort is that we do n work per level, and the total number of levels are, let's just quickly count. There's 1, 2, 3, 4, 5, 6, 7. Okay, it doesn't really matter what's the exact number. The takeaway is that there's a constant number of levels, each one doing n work. So we see that the total amount of work that merge sort is doing is n, right? Okay, so now what we notice is that we will be calling insertion sort, right? We will call insertion sort on n over 128, okay? And that's the equivalent, right? That's the equivalent of just calling insertion sort on n, right? Because we can ignore coefficients. So we can see that merge sort takes us n time, insertion sort or insertion sort on n, right? And how many times are we calling insertion sort on n? Well, how many nodes are at this level? Okay, what's the number of nodes? So if we actually want to calculate, there's probably around 2 to the 7 nodes at this level, okay? But I'm going to argue that the number of nodes on this level doesn't matter so long as it is a constant number of nodes, okay? So what we will notice is that each time we call insertion sort on one of these nodes, we are basically calling insertion sort on n. How many of these nodes are there? There's 2 to the 7. So the total amount of work we're doing for insertion sort, okay, the total amount of work we're doing is going to be around 2 to the 7 times the total amount of time it'll take us to insertion sort on n. And then we can kind of get rid of the 2 to the 7 because it's a constant. Okay, so how long does insertion sort take on n? Well, we know that in the best case, right, insertion sort takes us n time. In the worst case, it's n squared. So we see that the best case overall happens when merge sort takes n, right? Merge sort always takes n, and insertion sort takes n. The worst case happens when merge sort takes n, since merge sort always takes n, plus n squared. So we can see that the best case behavior is theta of n, and the worst case is theta of n squared. Okay, so we can put right here, the best case is, let's change. Actually, you can go in red, why not? Okay, perfect, that was a cool question. I am kind of proud of my work, so I will keep it. Nice. So let's move on to the next one. We can only swap adjacent elements in selection sort. So let's kind of look at an example to see how that would work. Suppose we have Let's zoom in again. Okay, suppose we have this array. Okay, let's say like 1, 2, 7, 4, 0, 3. Okay, if we recall how insertion or selection sort works, is that we iterate through each element. Okay, I'll quickly write down the algorithm again. First selection, sort. Okay, I'm not a huge fan of this. Let's make it a bit thinner. Okay, what we do is we find minimum, right? And then we move minimum to front, and then we repeat with remaining elements. Okay, and then we know traditionally that finding the minimum will take us n time. Moving the element to the front is constant, right? So our total runtime becomes, right? This traditional selection sort is n plus n minus 1 plus n minus 2 all the way up till 1. And the reason that we have this sum is that the first time it takes us n time to find the minimum. The second time it'll take us n minus 1 time. The third time it'll take us n minus 2 time, and so on. And the reason it takes us less time each iteration is that we're looking at less elements, right? The first time, in order to find the minimum, we look at 0 and it takes us n time, right? The second time, what we do is we move, right, 0 here and 1 here. And then in order to find the minimum, we look at n minus 1 elements, okay? So we get this following sum. Okay, so with this in mind, let's quickly look at one example. I'll try to like recreate a similar one as before, but it doesn't entirely matter. Okay, so now we can only swap adjacent elements. So our constraint is that we can only swap adjacent elements. Okay, so what this means is that moving the minimum to the front may take us more time than usual, right? Moving 0 all the way to the front means that we have to swap 0 and 5 and keep swapping 0 until it moves all the way to the front, okay? So what this is telling us is that moving the minimum to the front is now not a constant time operation, rather it can take, right, at most n time. Okay, so if we look at our total runtime, it's going to be all of the work that we were doing before. So let's call this our prior work, okay, plus our new work, okay? And this new work is going to come from moving the minimum to the front by swapping, okay? So the maximum amount of new work that we can do is going to be n the first time around, right? In the case that the minimum is always to the right, plus n minus 1, plus n minus 2, and so on, okay? So this is the maximum amount of additional work we can do by swapping, and the minimum is going to be like roughly constant, or we could say it's like roughly n work, right? In the case that the minimum is always over here, right? If the minimum is already in the place it needs to be, like we don't have to do really any more work. So we're going to say like a constant number of work, sure. The important takeaway is that if we're already doing, oh gosh, I didn't think it would be that big. Okay, if we're already spending n squared work in a selection sort, right, we notice that the added work by swapping is at most n squared, right? So we can see that if we're already doing n squared work and we are doing at most n squared additional work, the total runtime of our function doesn't actually change, right? The only way our function would actually change its runtime is if this added work that we're doing is greater than n squared, right? But if we're doing at most n squared work, then we're not actually changing the total runtime because n squared plus n squared is still n squared asymptotically. So with this in mind, we can see that the best case and worst case of selection sort is still n squared. Okay. Okay, so the next one states we can use a linear time median finding algorithm to select the pivot in quicksort. Okay, so let's quickly see how that's going to work. Okay, I'm going to move that a bit smaller. Just move it up here as like a nice collection of my work. Okay, so let's first, as usual, recall how quicksort works. So in quicksort, right, how it works is that we have some list. Okay, and the first thing we're going to do is choose a pivot. Then we partition about the pivot. Then we're going to call quicksort on the left half. And then we're going to call quicksort on the right half. Okay, so these are kind of like the steps to how quicksort works, right? And then we'll probably like, we could just say like quicksort of left half plus pivot plus quicksort of right half, right? That's kind of like the gist of the quicksort algorithm. Okay, so with this in mind, let's recall what the runtime of quicksort is traditionally. Actually, I'm going to shy away from doing that because it seems like a little unnecessary work. So let's just try to figure out what the runtime of this is right now. Okay, so we know that choosing a pivot, when we will use the median algorithm, will take us, okay, choosing a pivot will take us, let's put it on this left-hand side, n time. Okay, partitioning about the pivot will also take us n time, right? And then we call quicksort on the left half and quicksort on the right half. So with this quicksort algorithm, what we can realize is that we got a very similar recursive tree from the previous part. Okay, I'm going to quickly copy paste that. Okay, we're actually going to get the identical recursive tree that we got when we did merge sort. Okay, so what we're going to notice is that the total amount of work that we're doing, actually, it's very, very close to identical. But now, instead of doing n work per level, that's how we did in merge sort, now we're doing 2n. Okay, so what we're going to see here is that the total amount of work that we're doing at each layer in this tree is 2n at each layer. Okay, so with this in mind, what we can deduce is that the total runtime of quicksort when using a median finding algorithm is going to be the 2n, which is the number of layers, times log n, which is the height of the tree, right? Or actually, let's say the number. Okay, this is not completely correct. This is the work per level, and then log n is the number of the levels. Okay, so we see here that 2n is the work per each level, and log n is the total number of levels. So our runtime is going to be 2n log n, which is the same as n log n. Okay, so the last thing I kind of glossed over in this explanation is how in the world did we exactly get this recursive tree? Okay, so there was this egregiously loud noise in the background, so I paused it temporarily. Hopefully you guys could hear me in that short amount of time. Okay, so I realized I glossed over how we actually got this recursive tree. So what we're going to notice is that when the input size is n, we do 2n work for that call, and then we have a branch where we have 2 more recursive calls. Each recursive call is of input size n over 2, and we know the input size is n over 2 because when the median is the pivot, we equally partition all of the elements about the pivot, right? So quick example is suppose we have the following array, and we choose 3 as our pivot, right? And we're going to always choose 3 if this is what's given, because 3 is the median. What we realize is that the corresponding left and right are going to be of size n over 2, right? Because we know that all of the elements are unique, so a median will have an equal split. Okay, so we see here that we get this recursive tree, and we get a runtime of n log n. Okay, so we can put that as, okay, so for this one, it's n log n. Okay, and we know it's the best and the worst case because it always is going to take the same amount of time. If we have, ooh, that's a little, yeah. If we have a median time algorithm or a median finding algorithm, it'll always take the same amount of time because there's no ambiguity about the pivot we choose. Okay, so then this next one says we implement heap sort with a min heap instead of a max heap. Okay, so for this question, let's first recall how heap sort works. Okay, so let's first recall heap sort. Okay, so how heap sort works is that we start off with some array. Okay, so then what we do is we make this array into a max heap, right? Then what we do is we take this max heap and we sort it, and now it becomes sorted. Okay, so the process for making into a max heap is something called the bottom-up heapification, and it takes theta of n time, which is pretty cool. So the process of taking the max heap and making it sorted is this iterative process of remove max and placing max at end. Okay, so what that means is that if we have some max heap, let's say 7, 6, 5, 4, 3, 2, right? This is a max heap that looks like this. Okay, then what's going to happen in order for us to actually sort this array is that we remove 7, and then we're going to promote 2 to the top, and then 2 will bubble down accordingly. Okay, so how that looks is that we will have 6, 4, 5, 2, 3. And now what's really cool about heap sort is we have this vacancy at the end of the array. And what's amazing about that is now we have this open spot at the end of the array. So what are we going to put there? Let's put 7 there. And as we keep doing these steps of heap sort, a beautiful thing occurs where the size of this array, right, actually array slash heap, is going to shrink, and the size of the sorted, okay, the size of the sorted list is going to grow. Okay, so all we're really doing is growing this sorted list from this right-hand side. Okay, so now what we're going to realize is that in the problem, if we're not using a max heap, and instead we're using a min heap, what will happen is that every time we remove the minimum, we will put the minimum at the end of the array. Okay, so just to reiterate, every time we remove, let's see. Okay. Okay, so what we're going to notice is that every time we remove the minimum, instead of putting the minimum at the back, it would make more sense to put it at the front, okay? But if we wanted to put it at the front, we would have to shift all of the elements one to the right, and that's going to take a ton of time. So my idea is we can use a min heap, and we're going to create an array that's sorted in descending order, okay?
So using a min heap, if we keep adding the smallest element at the end, what we'll realize is that after running the same algorithm as before, what will happen is that this array will be sorted in descending order, right? Which coincidentally happens to be the same as the initial state of this max heap, right? So, right, so now the new algorithm, just to reiterate, it creates a min heap. Okay, let's just say it looks like this for the example, and then it sorts it in descending order. Okay, so now using a min heap, we need to reverse the ordering. So we're going to add in another step where we basically just reverse the ordering. Okay, so after reversing the ordering, what we're going to realize is that now the array is sorted in ascending order, or ascending order. I don't know, I said ascending order. Nobody talks like that. Okay, so since it's sorting in ascending order, let's look at the total runtime. So we have n and n log n from before, and the reverse operation takes n time. So we see the total runtime hasn't changed. It's just a bit more complicated. Okay, so what we're going to see here is that the worst case is n log n, and the best case and worst case are both n log n. Okay, so we have one more, and hopefully I can squeeze it in before my roommate comes back. Okay. This question states, we run an optimal sorting algorithm of our choosing, knowing there are at most n inversions, there's exactly one inversion, or there are exactly n squared minus n over 2 inversions. Okay, so every time we see the word inversion, the first thing that we should remember is that inversion sort takes data. Let's use a bit thicker. Let's make this. Data of n plus k time, where k is the number of inversions. So I recommend watching my past video, I think from last week, where I kind of explain why insertion sort's runtime is theta of n plus k, if you guys forgot why that's the case. Okay, so otherwise, if insertion sort takes theta of n plus k time, and we have at most n inversions, we know that if we run insertion sort, it'll take us at most theta of n time, right? And that's using insertion sort, right? Okay, so it seems to me that theta of n is a pretty good runtime, so I'm going to put it down for best and worst case. Okay, the worst case makes sense why it's theta of n, because insertion sort takes theta of n, right? But the best case, it seems to me that what if we can do better than theta of n? Okay, I'm going to make the claim right now that we cannot do better than theta of n just by the problem description. Okay, let me quickly charge my laptop so I can finish this video without it being dead. Okay, so I'm going to prove that we cannot do better than theta of n best case. Okay, so my reasoning in order for our algorithm to terminate, either there's two possibilities here. The first possibility is that we saw n inversions and resolve them, or we looked at every element in the array. Okay, so these are the only two ways for our algorithm to terminate, or any algorithm of that matter. Okay? And what we'll realize is that in either possibility, we will be doing n work. Right? So in either case, for any sorting algorithm it will do, we have to at least do n work. Okay? So we see that theta of n is the best case. Okay? Nice, that's pretty cool. So let's move on to the next one. I'm trying to encapsulate all of this amazing work. Okay. So for the next part, we have exactly one inversion. Okay. And I realize I haven't defined an inversion. So an inversion is when we have a pair of elements in an array that is out of place. Okay, so what does that mean? Let's say that we have the following array. Okay, and let's look at the pair of 7, 1. So looking at this pair, like the pair 7, 1, we realize that 7 is earlier in the array than 1, but it is bigger than 1. So we can say that this pair is an inversion. Okay, we can think of an inversion as something a sorting algorithm seeks to remedy, right? Because if this array is finally sorted, then we should have the case that for every pair of elements, the element on the left is smaller than the element on the right. So an inversion is kind of like a red flag for any sorting algorithm, right? This intuition. Okay, so if we have exactly one inversion, I'm going to argue that the best case can be, oh, what happened to my best case and worst case? Okay, the best case can be constant time and the worst case will be n. Okay, so suppose that our only inversion in the array are the first two elements, right? It takes us a constant amount of time to look at the first two elements. So what we'll realize is that the best case is constant when our only inversion is the first two elements. On the other hand, if our inversion is some point later in the array, let's just say that like it's at the end, we have to look at all of these elements, right? Need to consider first, right? And what we'll realize is that worst case, it takes us n time. And suppose that you say, hey, Soham, like, what if I started looking from this side? I would see this one first. Well, any algorithm, no matter how we look, there's no guarantee that we will find that inversion in a constant number of steps, right? For any sorting algorithm or any algorithm of that matter, it may take us at most or up to n time to find the inversion, right? So there is the worst case of n. Okay, so that is all for that question. Nice, so we're on the last one right now, and it states there are exactly n squared minus n over 2 inversions. So this question is rather tricky, and I'm going to approach it like a student just to give you guys a perspective of how this question is approachable on an exam. Okay, so suppose we have this array of size 4. Okay, so if we have the array of size 4, that's telling me that there is 4 squared minus 4 over 2 inversions. Right? In other words, they are exactly 6 inversions. Right? Okay, so if there's exactly 6 inversions, how can we create 6 inversions with the elements in this array? Okay, the first thing that I'd like to point out is that 6 is a lot of inversions in such a small array. So intuitively, we want to maximize the number of inversions in the array. Okay, that's like a guess I have. So what is the maximum number of inversions we can have in any given array? Well, let's look at, let's just say we have x, y, z, and then a. What is the maximum number of inversions that x can be part of as the leftmost element in the pair? So my question is, what is the maximum number of inversions where x is the leftmost element. Okay, so we notice that there are 3 of these inversions, right? xy, xz, and xa. And another jump that we can make after this point is that for any element in any array, it could potentially be the leftmost element in a pair, right? With every element that's later than it, right? Y can be part of inversions where it's the leftmost element with all of the later elements, right? So if we're looking at the total number of inversions in any given array, we can see that the first element can be part of 3, then 2, and then 1, and then 0 for this example. And what we can realize is that we can generalize n squared minus n over 2 into n times n minus 1 over 2, which is the same as the first. Actually, it's the same as the sum of the first n numbers, of first n minus 1 numbers. Okay, so why that's cool is that if we have the number of inversions equal to the sum of the first n minus 1 numbers, what that tells us is that in this given array, every single element is part of an inversion, the maximum number of inversions. Okay, so looking at this example, if we have, I'm just going to reiterate because it's kind of confusing. If we have n squared minus n over 2 inversions, that means the total amount of inversions is the sum of the first n minus 1 numbers. What that means is that they are the maximum number of inversions possible in the given array. Because the maximum number of inversions we can possibly have is n minus 1 plus n minus 2 plus n minus 3 all the way down till 0, right? That's the maximum number of inversions we can possibly have because each element can at most be part of an inversion with everyone to the right of it, right? So we see here that the maximum number of inversions in the array is the sum of n minus 1 all the way till 0, and we see that that sum is the total number of inversions that's given to us in the prompt. Okay, so with this in mind, all this is saying are there is the maximum number of inversions. So if we ever have an array that has the maximum number of inversions, what that tells us is that every element on the left is greater than everything to the right. Okay, so looking at this sample array, we see that 3 is greater than everyone to the right of it. 2 is greater than everyone to the right of it. 1 is greater than everything to the right of it. And what we notice about this array, right, this array that maximizes the total number of inversions, okay, is in descending order. Okay, that's a really, really cool idea, is that if we ever have an array that has the maximum number of possible inversions, we know for a fact that that array is sorted in descending order. Okay, so all we need to do is reverse the ordering, right? Reversing the ordering is a linear time operation. So what we can say here is that the best case is n and the worst case is n, because all we really need to do is reverse the ordering of this array because it's sorting in descending order and we want to sort it in ascending order. Okay, so that was a long video. I hope you guys enjoyed it. And yeah, thank you guys for watching as per usual.